Hello, my name is Daeyeon and I'm one of the co-leaders of ACT2, Prevention of Infection Transmission. The other co-leaders of this act are Mamie Coates from Alabama State University and Catherine Picard at Giant. Unfortunately, because I am on my sabbatical leave in Korea, I'm not able to attend this exciting kickoff symposium that is being held on December 7th at the Singh Center for Nanotechnologies. However, please rest assured that Act 2 is very vibrant. With the help of the other co-leaders as well as the members of Act 2, we have put together a very exciting proposal for research. And recently we have successfully recruited 2 fellows who are engaged in research projects that will bring all of us together. I hope you have enjoyed the symposium thus far and enjoyed the rest of the day. And hopefully I'll get to see all of you in the not too distant future. Thank you, and I hope you enjoy my presentation.
Okay, this is Daeyeon again, one of the co-leaders of Act 2, Prevention of Infection Transmission. The other co-leaders of the Act are Mamie Coates from Alabama State University and Catherine Picard at Grenoble IMP. The goal of this Act is to relate surface mechanics, texture, and chemistry to the adhesion, proliferation, and killing of microorganisms, in particular bacteria, to enable active coating technologies that suppress surface-mediated transmission of infection. To achieve this goal, we have assembled a team of researchers with complementary expertise, research interests, and facilities. There are a number of major risk factors that increase the possibility of infection transmission after a major natural disaster. For example, when emergency shelters are set up after an occurrence of a natural disaster, a large number of people are placed into a very confined space where sanitation conditions are quite poor. Because of the lack of clean water and adequate sanitation, microorganisms can grow and spread among a large number of people in a short period of time. Besides such natural disaster situations, our daily lives also present multiple possibilities by which infections can spread. Common surfaces, such as doorknobs and switches, can act as quote-unquote bus stops for germs between people. Also, we have all heard about horrific incidents of bacterial infections that occur at hospitals. Recently, the number of incidents of very aggressive strain of bacteria known as MRSA has been on the rise, and these cases have led to a significant number of fatalities and economic loss in the US. To reduce the possibility of contact or surface-mediated infection transmission, a number of researchers, including ourselves, have developed and studied various types of antimicrobial coatings. These are very thin coatings, often less than a few microns in thickness, that can, for example, resist the adhesion of bacterial cells on the surface. Also, there are active coatings that present antimicrobial functionality on the surface that can lead to cell killing. Another mechanism that has been studied in depth, as shown on the right, is the release of antimicrobial agents or chemicals that will lead to cell killing. More recent studies have even shown that active coatings that exhibit combinations of different cell-killing mechanisms can be developed or engineered. Our ACT will use 2 different strategies to prepare antimicrobial coatings. In one approach, developed by Roscomposto, copolymers are grafted onto surfaces to form what is known as nanobilayers. Such a film presents chemical moieties that can kill bacteria upon contact, and also release antimicrobial agents to kill bacteria. Another approach that has been used extensively by myself and co-leader Catherine Picard is to use layer-by-layer assembly between 2 associating polymers. By controlling the assembly conditions and using different types of polymers, it is possible to prepare antimicrobial coatings with a wide range of properties. In this act, we are particularly interested in using various types of natural polymers, such as chitosan, which is shown here, to form these types of active coatings. The reason that we are interested in using these types of natural polymers such as polypeptides or polysaccharides is because of their abundance as well as their biocompatibility. This slide shows some of the fundamental questions that we are interested in addressing in this act. In the next 6 or 7 minutes, I'll share with you why we became interested in these problems and what our plans are and how each member of the act will contribute to addressing these questions. We're very interested in understanding how surface mechanics will affect the adhesion and proliferation of bacterial cells on the surface. Interestingly, a large number of studies have shown that behaviors of mammalian cells, which by the way are very different types of cells compared to bacterial cells, depend critically on the mechanical properties of the cell surface. For example, a seminal study by our colleague Dennis Disher showed that the differentiation of stem cells depend on the stiffness of the surface. On a hard surface, stem cells become bone cells, whereas on soft surfaces, stem cells become nerve cells. There's much less understanding on the effect of the surface mechanics on the behavior or adhesion behaviors of bacterial cells. This study is one of the few studies that report that bacteria tend to adhere well onto hard surfaces. That is, fewer bacteria adhere to softer surfaces. However, all of these studies are not considering something that is central to the behavior of types of materials we'll be using to make our active coatings. Condensed matter can be classified into elastic solids or viscous fluids. Solids resist deformation and recover their original shape after being deformed, whereas fluids, on the other hand, will flow with little resistance and adapt the shape of their container. What people have previously shown is that the solid-like properties of surface affect bacterial adhesion. Now let me digress a little bit here and consider the mechanical properties of a cornstarch solution. The question is the mixture of cornstarch and water solid or liquid? Here's a very nice YouTube video that will give you the answer.
So, this is cornstarch and water, and when you bang it hard, you can get through. But when you go slow, you can't get your hand out. It reacts like a solid and a liquid. What's that word again? Viscoelasticity. I got some putty.
The student in this movie nicely explained something called viscoelasticity. As you just saw, cornstarch solution can behave like solid or liquid, and this depends on the rate of deformation. The faster you deform, the more solid-like behavior the solution exhibits. Interestingly, the molecular structure of cornstarch is very similar to the polymers that we are using to make our active coatings. It is quite plausible that our coatings will exhibit viscoelasticity. Also, it is known that cells themselves are viscoelastic. Thus, it is critical for us to be able to, number one, measure the viscoelastic properties of coatings, and number two, to relate viscoelasticity of surfaces to the adhesion and proliferation of bacterial cells. The question is, how does one characterize the viscoelasticity of a material? Usually, it's done using an instrument called a rheometer. Typically, the material of interest is placed in between two plates, and these two plates are rotated at different rates to study the material's response. However, because our coatings are typically very thin, it is not easy to use rheometers to characterize the viscoelasticity of our material. Ross Composto has recently developed a very nice method of using atomic force microscope to measure the viscoelasticity of soft material such as living cells. As you can see in this graph in the lower right corner, the viscoelasticity of cells indeed depend on the rate of deformation or the frequency of deformation that is being applied. We'll be using this approach to characterize our active coatings and then relate the viscoelasticity of the material to the adhesion of cells on the surfaces. Another important factor that has not been extensively studied in this area is the effect of surface roughness. Almost every surface we come in contact with has some degree of roughness associated with it. When a cell comes in contact with a rough surface, it is quite plausible that the cell has to make a decision on whether to stick or not to stick, depending on the size of hills and valleys it sees. To enable this study, we'll collaborate with researchers in Act 1. Xu Yang is the world leader in studying the effect of surface topography on wetting. We'll use her expertise as well as the expertise of Catherine Picard to create surfaces with well-defined roughnesses to understand how surface topography would affect cell adhesion and proliferation. While a number of studies have shown that many antimicrobial surfaces are very potent in killing cells via contact or release-based mechanisms, most of these studies were done using surfaces that were completely submerged underwater. Now, unless you're a mermaid, we don't live underwater. Thus, it is important for us to understand how partial hydration rather than full hydration, as well as dehydration of surfaces, would affect the effectiveness of antimicrobial surfaces. We'll be using various techniques to relate the effect of humidity on the release of antimicrobial agents and the orientation of cell-killing moieties on the surface using techniques such as confocal microscopy and fluorescence spectroscopy. In particular, we're very excited about the expertise of Dr. Remy Dreyfus of Solvay, who has done a lot of work on the hydration and dehydration phenomena in soft materials. As you saw in the previous slides, we're very interested in understanding the relationship between the surface properties or structure and cell adhesion and proliferation. To obtain more quantitative understanding, we'll use a variety of techniques developed by our colleagues at Giant at Penn to quantify the strength of adhesion of bacterial cells on various surfaces. For example, we'll use a flow channel as shown on the upper right corner, which allows us to precisely control the shear stress that is being exerted on the cell sitting on a surface. By using this channel, we'll study the adhesion strength of bacterial cells on the surfaces with different chemistry, texture, and viscoelasticity. Also, our French partners have developed a remarkable method of directly visualizing the interface between a cell and a surface using electron microscopy at the nanometer scale as shown in this lower right corner. We'll be using these types of methods to look at directly what the link is between individual cells and surfaces with different structure and viscoelasticity. It is also well known that bacteria develop resistance to antibiotics. Thus, it is quite plausible that bacteria will also develop similar resistance to engineered surfaces that are designed to kill them or resist their adhesion. To understand how cells respond to such stresses, it is critical for us to monitor how cells themselves change. And this change can be studied by analyzing molecules such as proteins, RNA, DNA that they make and secrete. Our colleagues at Alabama State, especially Mamie Coates, whose expertise is in molecular biology, will use RNA microanalysis methods to monitor how cells respond to engineered active coatings and what kind of resistance mechanisms they develop. Of course, all of these activities would not be possible without talented students and postdocs. And we are very lucky to have two superb researchers as the first cohort of our ACT2 fellows. These fellows have expertise and interests that are perfectly aligned with the goals of this ACT. Tagbo Nipa in particular will play a central role in leading the efforts in various outreach activities and organized student activities in the entire REACT. With that, I would like to conclude my talk by sharing our enthusiasm for this global scale collaboration that brings together expertise from Penn, ASU, and Giant. Although I haven't had a chance to discuss this in detail, we are also very fortunate to have the opportunity to work with our partners in Solvay, who will play a central role in enabling mass production of antimicrobial coatings we're studying. We are also very excited about working with a talented group of students and postdocs who will further strengthen our collaboration and ultimately understanding of how antimicrobial surfaces work to prevent transmission of infection in the human habitat. Thank you very much for your attention. And although I will not be able to answer your questions, I'm sure my colleagues who are present will be more than happy to answer any questions you may have. Thank you.